What if everything you knew about airplane wings was wrong? Boeing discovered something that broke every rule in aviation. They built wings so massive airports couldn't handle them. Then they solved it with technology from warships. The 777X carries a secret that airlines don't want competitors to know. A feature so revolutionary it needed special government approval just to exist. Here's what they're hiding.
And here we go.
Boeing launched the 777X program in November 2013 to develop two variants. The 777-8 provides seating for 395 passengers and has a range of 8,745 nautical miles. The 777-9 has seating for 426 passengers and a range exceeding 7,285 nautical miles. The 777-9 first flew on January 25, 2020. Boeing expects the first aircraft to be delivered in 2027 following years of certification delays. The program has accumulated approximately 500 orders from airlines worldwide despite repeated postponements. The 777X needed to compete directly with the Airbus A350-1000. Airlines demanded greater fuel efficiency to meet stricter environmental regulations while maintaining profitability on long-haul routes. The aircraft also needed to fit within existing airport infrastructure without requiring expensive gate and taxiway modifications. Boeing pulled technology from the 787 Dreamliner, including composite wing construction and cabin improvements and advanced systems. The 777X represents Boeing's effort to create a bridge aircraft between current generation widebodies and future aircraft designs. The 777X is the first commercial aircraft in history with folding wingtips. This represents a breakthrough in commercial aviation design. The massive carbon fiber composite wing has an ultra-high aspect ratio for efficiency. The wingspan measures 235 feet 5 inches from tip to tip when fully extended. However, the tips fold upward on the ground, reducing the wingspan to 212 feet 9 inches. This allows the plane to fit into existing airport gates designed for Code E aircraft, like the current 777 models. The wing is based on the 787 wing design but with less sweep. Boeing increased wing area from 4,702 square feet on previous 777 models to 5,562 square feet on the 777X. The aspect ratio increased from 9 to 1 to 10 to 1. This higher aspect ratio increases lift production while keeping other factors like speed and thrust constant. The wings curve upward towards the root and downward towards the tips. The shape changes airflow over the surface to reduce drag, thereby improving fuel consumption and efficiency. The folding mechanism was manufactured by Liebherr Aerospace. The wingtips measure 11 feet in length. When the switch is flipped, the wingtips lock in the takeoff position within 20 seconds. After landing and slowing past 50 knots, the wingtips automatically begin to fold. Pilots monitor the orientation through new iconography on the engine indicating and crew alerting system display. The system illustrates the tips in transit and folded and deployed positions. Boeing needed FAA approval for this novel feature. Existing regulations did not cover folding wingtips. The FAA issued special conditions in May 2018 covering worst-case scenarios. The conditions required proving load-carrying limits and demonstrating handling qualities in crosswind conditions when raised. The FAA demanded that all sources of airplane power that could initiate unlocking of the wingtips must be automatically isolated from the folding system prior to flight. The wingtip latching and locking mechanisms must be designed so that under all airplane flight load conditions, no force or torque can unlatch or unlock the mechanisms. The folding design alone improves fuel efficiency by approximately 10% compared to previous 777 models. This represents massive cost savings for airlines operating long-haul routes. The bigger wings in the air provide superior aerodynamic efficiency. The smaller footprint on the ground allows the aircraft to use existing infrastructure worldwide. Airlines can upgrade their fleets without forcing airports to rebuild terminals or expand gates. This breakthrough makes the 777X commercially viable for carriers operating at space-constrained airports. Powering the 777X is the GE9X. This is the largest and most fuel-efficient jet engine ever built. General Electric invested more than $2 billion in development. The engine features a fan diameter of 134 inches. This diameter is larger than the fuselage of a Boeing 737. The GE9X is rated at 110,000 pounds of thrust. The engine achieved a world record thrust of 134,300 pounds during testing in November 2017 at GE's Peebles, Ohio facility. This broke the previous record of 127,900 pounds, set by the GE 9115B in 2002. The GE9X features 16 carbon fiber composite fan blades. The GE90 predecessor featured 22 fan blades. The reduced blade count maximizes airflow and minimizes drag, contributing to fuel burn and noise emission advantages. The fan blades feature steel leading edges and glass fiber trailing edges to better absorb bird strikes. The composite materials provide strength while significantly reducing weight. The engine uses ceramic matrix composites in the high-pressure turbine section. These materials embody high-temperature tolerance that allows for greater efficiency and reduced cooling needs. The GE9X achieves a 10-to-1 bypass ratio. The overall pressure ratio reaches 61-to-1 compared to 40-to-1 on the GE90. This massive pressure ratio considerably lowers thrust-specific fuel consumption. The engine delivers 10% better fuel efficiency compared to the GE90. This improvement provides 5% lower thrust-specific fuel consumption than the Rolls-Royce Trent XWB-97 powering the Airbus A350. Annual fuel savings due to the GE9X having 10% less fuel consumption versus the GE90 equals approximately 3,000 metric tons of fuel per aircraft. This translates to roughly 9,500 metric tons of CO2 reduction, equivalent to removing approximately 2,060 cars from the road. The engine produces half the nitrogen oxide emissions of any engine in its class at a level less than half of current regulatory requirements. All emission values meet or exceed current regulatory requirements with 50% lower emissions for carbon monoxide and particulate matter and nitrogen oxides. The GE9X represents the quietest turbofan engine per pound of static thrust GE Aerospace has ever produced. The engine is designed to meet current and anticipated next-level noise certification standards. The GE9X features advanced technologies throughout its design. The twin annular pre-swirl combustor improves fuel efficiency and reduces emissions by mixing fuel and air more effectively. The engine uses full-authority digital engine control, providing advanced diagnostic and operational capabilities. The control system ensures optimal performance and simplifies troubleshooting and maintenance. GE employed 3D printing for parts that would be impossible to manufacture using traditional techniques. The compressor features blisks in the first 5 stages, combining bladed discs instead of traditional separate fan blades. Inside the 777X introduces cabin improvements derived from the 787 Dreamliner. The internal cabin width increased from 231 inches on previous 777 models to 235 inches through thinner interior cabin walls and better insulation. This allows 18-inch wide seats in 10 abreast economy configuration. The aircraft features larger windows and higher ceilings, and more humidity and lower cabin altitude compared to previous 777 variants. These improvements bring near Dreamliner comfort to high-capacity routes. The cabin maintains higher humidity levels, reducing passenger dehydration on long flights. Lower cabin altitude equivalent to approximately 6,000 feet compared to 8,000 feet on older aircraft reduces passenger fatigue. The larger windows provide better views and more natural light. The combination of these features significantly enhances passenger experience on ultra-long-haul flights exceeding 15 hours. The 777X cockpit mirrors the 787 with large displays and head-up guidance and dimmable windows and dedicated folding wingtip controls. Touchscreens replace older cursor systems, while an optional tail-mounted ground camera can even stream wingtip-to-wingtip views to cabin screens. In performance terms, new engines deliver about 10% efficiency gains with longer composite wings, adding roughly 7% partially offset by a heavier structure. The net result is a 12 to 13% fuel improvement and up to 20% lower fuel burn per seat. Long-term, the 777X proves large wide bodies can be efficient and sustainable and profitable well into the 2040s.